Good morning, my most amazing students. Buenos dias, mi fabulosos estudiantes. I hope you all had a really good spring break. I wish we were back in the classroom, but until we see each other again, this will have to do, okay? Our learning must move forward. Here you can see before you, I have a PowerPoint, and I'm just going to kind of do a recording behind it because what I tried to do earlier did not work. You guys could not hear the sound, so hopefully this works. All right, what do we have here? We have linear and non-linear functions. That is going to be our learning target for this week. I want you to be able to determine the difference between a linear and a non-linear function. Okay, so keep that in mind. That's our learning target. All right, before we move into our learning target, I want to do a quick review on what is a function. Okay, that's where we left off before we went to spring break. And we kind of have to pick up there before we can move forward, okay? So I want you to remember a function, and I know this says a relation, but in class we use the word rule, okay? So I'm going to put the word rule back in here instead of relation. So a function is a rule in which for every input there is exactly one output, okay? So that's kind of what we're looking for to determine if something is a function. For every input there has to be exactly one output. Now, we have some characteristics that we can look for when we're looking for a function. So this is a graph right here. And so when we see a graph, we can see if it passes the vertical line test. Remember the vertical line test, if you hold, let's see if I have this pencil here and I have a vertical line and I scan that graph from left to right, it only passes the graph in one spot. And if it only passes it in one spot, touches it in one spot, it is a function. Now, if it crosses it in more than one spot, it is not a function. Now, this isn't a great example because it's kind of small on the screen, but I will show you more examples as we move forward, okay? But you should remember that before we went on spring break, we went through a bunch of graphs and we determined which ones were functions and which ones were not functions, okay? This is also an example of what a function would look like, a linear function to be exact, because if you were to connect those dots, it would create a straight line. So that would actually be a linear function. I think we learned the most, though, from this non-example. If you'll remember before we left, I talked about a function being a machine. So if we go up to that machine and I press a 2, I want to be able to press a 2 and get the same thing out every time. Well, this is not a function because if I press a 2, I get out a 3. If I press a 2, I get out a 5. That's a broken machine. We don't like that. We want a machine that when I press a 2, I'm going to get the same number out every single time, okay? For every input, there is exactly one output. Well, that's not true. There's 2 outputs here. So this is not a function. Okay. All right, let's go to the next one. So we have linear versus nonlinear. We're going to look at this in 3 different aspects. We have a table, a graph, and an equation. So if you see a table there, here's how we determine if it's linear. So here's what it says. A table is linear if the rate of change is constant. So if we have a table with input and output values, our x and our y, we want it to be constant on both sides. So +1, +1, that's great. That's the same rate of change. And then over here, +5, +5. And I'll tell you what I mean. So we go from 0 to 1, what are we doing? We're adding 1. We go from 1 to 2, what are we doing? We're adding 1. And if we kept going with that table, it would be the same pattern over and over, okay? And then over here for the output, it's the same pattern. Add 5. To go from 5 to 10, you have to add 5. To go from 10 to 15, you add 5. So if we have the constant rate of change, that would be a linear function, okay? Now, if we're talking about a graph, here's what it says. A graph is linear if it is a straight line. So you'll see this example of this graph right here, and the one that was the previous slide, it was a straight line. That is a linear function. Now, these graphs that you're going to look at, they're all going to be functions, but some are linear and some are not, okay? And then last but not least, we have an equation. An equation is linear if the power of x or y is either 1 or 0, and they appear in the numerator and they are not multiplied together, okay? And we'll take a look at this here in a minute and see what I'm talking about. But basically what you need to keep in mind is when you see that x and that y, we want it raised to the power of 1, which just means 1x or 1y. We do not want to see x squared or x cubed or y squared or y cubed, because when we see that, that's our indicator that it's no longer going to form a straight line. It's going to be a function, but not a linear function, okay? And that'll make more sense here in a minute when we get to the next slides. Okay, So I wanted to give you some examples of some tables. So I'm going to go ahead and turn here and we're going to look at this first. I'm going to see if I can zoom in and look at this first table here. So if we look at this first table, you can see that it says it's linear. It says that it has a constant rate of change, and you can actually see that that is true. Going from 3, 6, 9, 12, what are we doing? We're adding 3 each time. To go from 12, 10, 8, 6, we're not adding 2. It should not say add 2. It should say subtract 2. So we're subtracting 2 each time, okay? So that is a constant rate of change. Now over here, what we have is an example of something that you would see that's nonlinear. So this one right here, example 2, says it's nonlinear. It's a varied rate of change. So watch what happens. Up here on the input side, 1, 2, 3, 4. That's a constant rate of change. Yeah, we're adding 1 each time. But what happens down here at the bottom? We're adding 3, we're adding 5, we're adding 7. That's a varied rate of change. So that's going to indicate to us that if we were to graph that, it would not be a straight line. Therefore, that is not linear. Okay? And then last but not least, we actually have this number 3 example. I'll see if I can get the camera over there. It is also linear. You can see that it has a constant rate of change. And that constant rate of change on the input side is actually plus 5. Okay, so we can see that right there. To go from 5 to 10, 10 to 15, 15 to 20, what are we doing? We're adding 5 each time. And then on the bottom, 13, 28, 43, 58, we're adding 15 each time. So constant rate of change, this is linear. Okay, so just to recap before we move on to the rest of our examples, see if I can get the camera back on this whole page. Basically what you need to keep in mind that if you're looking at a table, we want constant rates, both input and output values, okay? Or sorry, for the input and the output values. If you have a constant rate of change up here, but it is not a constant rate of change down here, it is not linear, okay? All right, let's go to the next slide. So zoom out a little bit so we can see this. So we now have graph examples. So when we're looking at a graph, I want you to be able to determine if that is linear or nonlinear. To get my camera situated just a second, guys. Okay, so let's look at example number 7. First of all, you can see right away there is a curved line there. So this is not linear. It makes sense. It's pretty basic, right? Number 8 is linear. It is a straight line. So when you say linear, I want you to be thinking straight line. That one's linear. This one is nonlinear. It's a curved line. So very simple, very basic. You're just looking at the graph, determining if it's linear or nonlinear based on what you see. If you see a curved line, nonlinear. If you see a straight line, it's linear. Okay. And last but not least, we have equation examples. So what happens if you see an equation? How are you going to be able to determine if that's linear or nonlinear? So we have this first example right here. Y equals 3/4 x plus 1. This is linear. It has no exponent. So do you see that 3/4 x? That x is raised to the first power. We don't put that there, but it's raised to the first power, therefore it's linear. Now, if that x was x squared or x cubed, then it would not be linear. But because it's only raised to the first power right there, that equation is linear. Okay, and then we have example 11. We started out with an equation that was not in slope-intercept form. xy equals 10. To get it in slope-intercept form, we want that x to go away, so we're going to divide by x on both sides. And we now have the equation y equals 10 over x. Now, this is something you're just going to have to remember, that if you have a if you have a variable in the denominator, that is nonlinear. We do not want a variable in the denominator, okay? Because what that means is this is division, and we do not want division with the variable in the denominator. If you were to actually put this in Desmos, so you guys have that option. You have Desmos calculator. In fact, let's go back to this one right here. I put that one into Desmos, and I know you can barely see it, but that is a straight line. It is linear. It has a positive slope. It's actually what we call increasing, okay? But look over here. When I put this one into the calculator, and you don't have to take my word for it, do it. Put it into desmoscalculator.com. And you're going to see right here, the graph looks like this, and the graph looks like that. There's a curved line there. That is not linear. All right, and then last but not least, we have this equation. Let's see if I can get it to see this real quick. We've got this equation right here, y equals x squared plus 3. It's nonlinear. It has an exponent. That x is being raised to the second power. Therefore, that graph, I'll see if I can zoom in so you can see it. That graph right there is a U-shaped. It's very faint. It's hard to see, but it's a U-shaped. So that creates a curve in our graph, and therefore it is non-linear. Count how many times I say that word, linear, non-linear. Okay, now that you understand the difference between linear and non-linear, I have an assignment for you to do for this week. Okay, it is going to be on Google Classroom. There are 9 problems. 1, 2, 3, 4, 5, 6, and then I'll have to go to the next slide. But you guys actually have it. Oh, I don't have the next slide. Oh, yeah, I do. There it is. 7, 8, and 9. So there's 9 questions that you have to get done by Friday. So what are these questions asking you? Well, here's what it's saying. Determine whether each table, graph, or equation represents a linear or nonlinear function. So taking what you just learned from the PowerPoint, I want you then to say, number 1, linear, nonlinear. And then I want you to give me an explanation. Tell me why you chose linear or nonlinear, okay? So all 9 should say linear or nonlinear, and there should be like 1 sentence telling me why you made that decision. Okay, and then there's going to be a second assignment there on Google Classroom. I want you to create a mini poster. I want this mini poster to have 3 different examples, a table, a graph, and an equation showing me the difference between what linear looks like and what nonlinear looks like, and that is also due Friday. So we've got 2 assignments to do, and they are both due Friday. Okay, I hope you guys have a great week. If you have any questions, be sure to email me, and I will see you soon. Peace out.